How Newton might have perceived gravity was sufficient to permit us to travel from Earth to the Moon at any given moment. Find yourself lost in the ticking rhythm of time, considering whether our understanding of it is just the peak of the enormous iceberg that lies on its surface. Revelation isn't merely a theory. A key could open the doors to the universe's mysteries, revealing a universe far more intricate and inspiring than we ever imagined. How does Brian Cox's recent theory challenge our traditional grasp of time? And what could it mean for how we perceive reality? Join us on an engaging investigation of the annals of time itself as we delve into Brian Cox's groundbreaking new hypothesis on the nature of time in the expansive cosmos around us. Secrets await discovery, and some of these secrets revolve around baffling notions of gravity and time, essential components of our existence. Picture a world where time behaves oddly. It can slow down or speed up, and the force that holds us in place on the ground may not be what it seems. This is the domain of Einstein's theory of relativity, where our interpretation of time and gravity takes an unexpected turn. Albert Einstein, a famous figure, gave us a novel way to view the universe through his relativity theory. His work established the basis for understanding how time functions in various contexts, especially when moving. The journey began in the early 1900s when Einstein proposed two revolutionary theories: the special theory of relativity and the general theory of relativity. The special theory of relativity, released in 1905, transformed our perception of reality. Simply put, it tells us that the laws of physics are the same for all observers who aren't accelerating their motion. This theory introduced the concept of relativistic phenomena, including the fascinating idea that time can stretch or shrink depending on specific circumstances. One fascinating thought experiment used to demonstrate time dilation is the light clock. Imagine being in a spaceship that is moving at near light speed. Inside the spaceship, a light beam is moving back and forth between two mirrors in a direction opposite to the ship's movement. According to physics, the speed of light is constant for all observers, so the light beam must appear to move along a longer angled path. The time it takes for the light to complete its journey should be the same for both the observer inside the spaceship and the one watching from outside. However, because the light must traverse a longer distance, it appears to the outside observer that it takes more time. This apparent difference in time between the two observers is what Einstein called time dilation. Time slows down for the observer in motion relative to the stationary one. In this case, time behaves in an unpredictable way depending on velocity. The concept of relativistic effects is more than just theoretical. Researchers use advanced instruments like particle accelerators, such as the Large Hadron Collider, to accelerate particles to incredibly high speeds, close to the speed of light. When objects travel at such high speeds, we must consider time in a special way to make precise measurements and predictions. Einstein's special theory of relativity, formulated in 1905, altered how we understand the universe, particularly with regard to motion and time. This theory challenges our normal thinking. It states that the fundamental laws of physics are the same for all, regardless of whether they are in motion. This is quite different from our everyday experience, where we might assume that adding speed to a moving object makes it go faster. However, Einstein's theory asserts that nothing can exceed the speed of light. This is the ultimate speed limit. From this viewpoint, events that seem simultaneous for us may not appear the same for someone traveling at nearly light speed. Another concept stemming from this unique perspective is length contraction, which means that when something is moving, it appears shorter in the direction of motion when observed from a stationary point. Additionally, the famous equation E equals mc squared reveals how energy and mass can transform into one another. This is crucial for understanding how tiny particles behave when moving rapidly and also for things like the process of nuclear fission. Special relativity is not just an abstract theory. It's something we use in common technology like GPS. When GPS satellites transmit signals to your device, they are moving, and because of their movement, time behaves slightly differently for them. If we didn't take into account these effects of time dilation in GPS calculations, your navigation would be inaccurate. So, special relativity teaches us that time isn't constant everywhere and for everything, it depends on how things are moving. This idea challenges our basic understanding. In fact, it's like saying the laws we use to explain the universe are incomplete. According to the special theory of relativity, Time isn't fixed. It's influenced by motion. Key concepts like the speed of light remaining constant and the interconnectedness between mass and energy have been demonstrated in a variety of experiments. But there's more. Enter Albert Einstein's general theory of relativity, proposed in 1915. This theory explores the deep connection between gravity and the structure of the universe. It changed the old idea that gravity is merely a force that pulls things at a distance. Instead, it explains that gravity is caused by the bending or curving of spacetime by objects. It's like saying gravity isn't a mysterious force, it's just how objects naturally move through the universe. According to Brian Cox's interpretation of general relativity, this means thinking of the universe as a four-dimensional entity, combining three spatial dimensions and one time dimension. In this framework, large objects like stars, planets, and even us influence the shape of reality around us. This creates gravity. Imagine spacetime as a large, stretchy fabric. When Earth-sized objects are placed on it, they create a depression. If you place a smaller object like a ball near this depression, it will roll toward it. This is how objects respond to gravity, not due to a mysterious force, but because of the bending of spacetime. General relativity offers a thorough explanation of how things move within our solar system. For example, it accurately predicts how planets orbit the Sun. Earth's elliptical orbit around the Sun can be precisely predicted by the theory. Brian Cox points out that this is a stark contrast to the old idea of gravity simply setting things in motion, which struggled to explain planetary movements. The revolutionary insight is that spacetime is curved like a flexible fabric, and this concept aligns with our observations of the universe. We observe an important confirmation of general relativity that came during a solar eclipse in 1919. Sir Arthur Eddington led an expedition to observe how light from distant stars shifted as it got closer to the Sun. According to the theory, the Sun's mass should cause the light to curve slightly. During the eclipse, the observations confirmed Einstein's predictions, providing significant evidence for the theory. Just as motion can alter our perception of time in accordance with special relativity, gravity also impacts time. In areas with intense gravity, time moves more slowly compared to regions with weaker gravitational pull. So, if you were near a massive object like a black hole, your clock would tick slower than one situated far away from the immense mass. General relativity introduces the concept of black holes, regions where gravity is so strong that nothing, not even light, can escape. The boundary around a black hole is called the event horizon, which denotes the point of no return. Once an event occurs within this boundary, it gets drawn into the black hole with no way to escape. Einstein's general theory of relativity has major implications for the structure of the universe. Initially, Einstein introduced a cosmological constant in his equations because he thought the universe was static. However, when scientists discovered that the universe is expanding, he later called this a great mistake. The concept of an expanding universe, based on general relativity, forms the backbone of the Big Bang theory, which explains the origin of the universe. Another important idea from general relativity is gravitational waves, ripples in spacetime created by extremely massive objects, such as merging black holes or neutron stars. In 2015, the Laser Interferometer Gravitational Wave Observatory (LIGO) detected gravitational waves for the first time, offering further proof of Einstein's theory. Over the years, scientists have conducted numerous tests to examine how general relativity works, and it has consistently stood up to scrutiny. Whether through studying planetary motion, observing the bending of light, or detecting gravitational waves, general relativity remains a robust theory. However, some scientists question and challenge established hypotheses regarding gravity. One alternative theory is called modified Newtonian dynamics, (MOND), which suggests that gravity behaves differently at low speeds, particularly within galaxies, without requiring the existence of dark matter. Instead of adding unseen material, MOND proposes that gravity strengthens at low speeds. The gravity debate also involves the elusive concepts of dark matter and dark energy, which were introduced to explain certain cosmic phenomena. Critics argue that these concepts may not be necessary and that alternative theories could explain observations. Some scientists reject Einstein's theory of gravity and explore other potential explanations, such as unknown particles or forces that might refine our understanding of gravity. It is important to note that new ideas in science undergo rigorous testing to determine their validity. For example, Einstein's concept of time as the fourth dimension, where time travel may be constrained by the speed of light, has been creatively linked with ideas like wormholes, hypothetical shortcuts in spacetime. Stephen Hawking's chronology protection conjecture suggests that traveling back in time is improbable from a physics standpoint. Ongoing experiments and observations aim to determine whether these new theories can explain gravitational phenomena in ways that align with established knowledge. While various theories have been explored, none have convincingly replaced the well-supported principles of gravity. Questioning and testing established ideas is fundamental to scientific advancement. These investigations provide comprehensive insights into the universe. As for gravity, general relativity remains the most significant and well-tested theory to date, explaining various phenomena such as the movement of planets and the bending of light around massive objects. General relativity holds strong because of its explanatory power and simplicity. Numerous observations, such as the way planets orbit the Sun, support Einstein's theory. Einstein's special theory of relativity also reveals that time behaves differently depending on one's motion. Let's explore how this impacts practical scenarios, especially in space travel. Space exploration is thrilling but immensely challenging due to the vastness of space. Moreover, according to Einstein's theory, the maximum speed anything can reach is the speed of light. This limitation creates a formidable challenge for space travel, especially when trying to reach the nearest stars given the immense distances involved. To better grasp what happens to time during space travel, we can consider the famous twin paradox. In this thought experiment, one twin stays on Earth while the other embarks on a journey to a distant star at high speed. When the space-traveling twin returns, they find that they have aged significantly less than their twin on Earth. This means they have effectively traveled forward in time. Time plays a critical role in space exploration because, over long journeys, time slows down for those traveling at high speeds. If astronauts were to visit nearby stars, time dilation would become more noticeable. They would age more slowly than those remaining on Earth. Although this may seem like science fiction, it is a real effect predicted by the theory of relativity. Imagine a mission to a distant star system. Given the vast distances involved, such a journey would take many years, even at high speeds. The spacecraft's crew members would experience time more slowly compared to those on Earth. This time dilation effect impacts both living beings and technology. For instance, GPS systems and communication satellites in space must account for time dilation to function properly. If they didn't, we would experience inaccurate positioning data. Space travel also presents a range of challenges, including exposure to cosmic radiation, the mental effects of isolation, and the physical impact of long-term confinement. In our daily lives, we can observe the effects of time dilation in systems like GPS. These systems require exact timing from satellites in motion, as time is experienced differently by satellites compared to people on Earth. Failing to account for these differences would result in inaccurate navigation. Finally, let's explore why time seems to flow in one direction. Time controls our existence, moving from the past to the present and into the future. But why does time move forward? This is where the concept of entropy comes in, an idea that measures how disorder or randomness increases over time. There is a strong link between the arrow of time and entropy. The second law of thermodynamics asserts that in any closed system, total entropy will either increase or remain constant. In simpler terms, entropy naturally increases and never spontaneously decreases. This growing disorder helps explain the one-way flow of time, as we observe in everyday events like ice melting or a stirred cup of coffee becoming chaotic.